who is speaking. Thanks a lot. And I have to apologize for the somewhat hasty preparation of the slides. This is a new thing for me. This is the first time I'm giving this talk, and the preprint is still very much a preprint. It's a fairly new thing that we have been doing. For Richard, it's not that new, but I will focus here on the results that have been done over the last couple of years. So all of this begins with really basic directed graph theory. Oh, and yeah, I should say the link I've posted to the link to the slides I've posted in the channel, and that contains a link to the preprint as well, which I guess I can also post on the channel, where you can read up the details, which might and might not be worth reading. So let me recall some basic definitions about directed graphs, because everybody has these words in a slightly different meaning. A digraph is a pair of a finite set of vertices and a set of arcs. And an arc here is just a pair of two vertices, nothing more, nothing less. In particular, there cannot be any parallel arcs because it's a set, it's not a multiset. But we can have loops and we can have anti-parallel arcs. So you can have arcs going one this way and the other backwards. Every digraph has a complement, which I call d bar. And that is just the digraph is the same vertices, but basically with all the arcs removed and all the non-arcs added as arcs. So what was an arc is no longer an arc, but what was not an arc is now an arc. So here is an example. Here is D, a typical digraph on three vertices, and here is its complement D bar. So for example, you see that D bar has a loop 1 to 1 because D has no such loop. But D bar has no loop from 2 to 2 because D has a loop from 2 to 2. And similarly, all the other arcs are defined. So everything that was here is no longer here, and everything that was missing is now added. And this is the formal way to write down those digraphs. So loops are not going to be important in this talk. Really, I could just as well not have them at all, but it's easier to use. The notations for loops are somehow easier than the notations without them. Anyway, a digraph is loopless if it has no loops, so no arcs from U to U. Now, what is a tournament? A tournament is a loopless digraph with the following property. For any pair of distinct vertices U and V, if there is an arc from U to V, then there is no arc from U to V, from V to U. And if there is no arc from U to V, then there is an arc from V to U. So you can think of it this way. A bunch of people play matches against each other. Each match is won by one of the two players, and the other player loses it. A tournament is a way to do it where every pair plays exactly one match, and each match is lost by one player. In other words, if you like undirected graphs, you can think of a tournament as a complete graph where you have given to each edge an orientation. And I think lots of people kind of ignore this kind of digraphs because they're so simple and the definition is so easy. Like, what can you do with them? Quite a few things. For example, there are a few proofs of a de Vandermonde determinants using tournaments. So if you want to prove the Vandermonde determinant combinatorially, this is a tool. But of course, the Vandermonde determinant is an easy thing that doesn't really need another proof. So I should, yeah. This is the thing. This is why I was trying to get the pages right. So this is an example. This is a bunch of examples. This is a tournament. This is a tournament. You might not see it immediately, but this arc has been flipped from here to here. This is not a tournament because 1 and 3 have not played against each other. And this is also not a tournament because each game has only one winner. Right. So here is a little bit more about directed graphs that, again, if you know graph theory, you will find it pretty obvious and not worth talking about. So the notion of a Hamiltonian path, I will define it in the following way. If V is a finite set, a V listing means a way to list all the elements of V, each of them only once. So people often used to call it a permutation of V, but nowadays permutation means something slightly different. Nevertheless, just as for permutations, the number of the things is size V factorial. Now, a Hamiltonian path in a directed graph is a V-listing, so it's a listing of its vertex set, where every two adjacent entries form an arc from the, so Vi to Vi plus 1 is always an arc. In other words, if there is at least one vertex, this is the same as saying it's a path of the digraph that contains each vertex. Now, some of you might remember this nice little theorem that any tournament has a Hamiltonian path. And I abbreviate Hamiltonian path by HAMP because I use this word a lot. So this is often done as an easy exercise in the graph theory class. And it's credited to Redei, but people don't usually remember what Redei actually proved. This is the least interesting thing of what he did. In the same paper, he proved something weirder. He proved that the number of Hamiltonian paths in the tournament is always odd. And of course, an odd number is positive, so this implies that any tournament has a HAMP. So if you can prove this, then this follows automatically. So here is a bunch of examples. It's probably worth taking a bit of a look at this. So this is a tournament with only one HAMP, because you have to start at 1. You cannot get to 1, so you have to start at 1. Then you have to go to 2, because if you go to 3, you're immediately stuck. And then after 2, you have to go to 3. So 1 to 3 is a Hamiltonian path of this tournament, and there is no others. This tournament has 3 Hamiltonian paths: 1 to 3, 2, 3, 1, 3, 1, 2, because it's a cycle. To turn a cycle into a path, all you need to do is you just break it at any point you wish. So you get 3 of them. This tournament, so you have a 4 cycle and 2 more arcs. This tournament has 5 HAMPs. The obvious one is 1, 2, 3, 4. And of course, it's cyclic rotations. Do you see, anyone sees another? Redei says that the number is odd, so there has to be another.
2, 4, 1, 3.
2, 4, 1, 3. Yep. 2, 4, 1, 3. Yes. And I think that's it. At least I had my computer check that there is only 5. Maybe I mistyped something, but I think it's true. And here is one with 9 HAMPs. So you can, if you can spend a while looking for something with 8 HAMPs or 6 HAMPs. It doesn't happen because of the theorem. Redei's proof is complicated and pretty intransparent. He uses determinants, but somehow he uses them in a way that I barely understand as a combinatorialist. So it's much more than determinants as it goes in there. And even so, John Moon has kind of translated this proof into English. It's not really clearer in his writing. So somewhere in the 70s or maybe before, Berge has been, I think he was basically trying to make this proof, to make this theorem available for his textbook, because he was writing a textbook on graph theory. And so he found a better proof. His proof uses another theorem, which in itself is pretty interesting. This is not about tournaments anymore. This is about any digraph. And the claim is the Hamiltonian path of the complement and the Hamiltonian path of the original digraph, well, they're not quite in bijection, but their numbers are congruent modulo 2. So for example, here is a digraph with 3 HAMPs, and here is its complement, and that complement has 1 HAMP, 1, 3, 2. And 3, of course, is congruent to 1 modulo 2. Now, even so, how does this help? It's not obvious. First of all, it's not obvious how to prove this Berge theorem. And secondly, it's not obvious how to prove the Redei theorem using Berge. And maybe this non-obviousness is the reason why people don't usually learn about them in undergrad. But actually, it's not that hard anymore. The proof of Berge theorem uses some kind of inclusion-exclusion argument. Pretty tricky. I think so. I'm going to say something vague. I'm going to say that it reminds me a lot of Fouatta's fundamental bijection, but it's not exactly Fouatta's fundamental bijection. It's an inclusion-exclusion argument to begin with. And then he uses this Berge theorem to prove Redei's theorem by induction on the number of inversions. So what is an inversion? Well, basically, you begin with a tournament where every arc goes upwards, and then you start flipping those arcs to go wherever you want. So it's a much nicer proof. It's made it into several textbooks, but it's still not very simple. So before I go on to actually algebraic combinatorics, let me say something very strange. This has been a mass overflow question that has been answered a few years ago. And by answered, I don't mean answered, I mean partially answered. The mystery gets deeper every day. So Redei says that if D is a tournament, the number of hemps is odd. But is this all you can say? Can it be any odd positive integers? Well, people have tried, and with some kind of sort of intelligent brute force, it has been found that 7 and 21 are not reachable. So there is no tournament with 7 Hamiltonian pairs, and there is no tournament with 21 either. Apart from that, any odd number between 1 and 80,000 is reachable. And of course, it makes me wonder whether these are the only exceptions. Nobody knows. So if you're looking for a pretty tantalizing open problem in graph theory, here is one. I would love to say that whatever comes next has some kind of use in that, but I don't know. I don't expect that to be useful necessarily. Now, here is another strand, which I think has been originally completely independent of this research. Basically, Chow in 1996 has been generalizing a certain graph polynomial found by Chang and Graham called the cover polynomial to do some Rook theory with it. Of course, Rook theory is directed graphs by another name because a Rook, so a board in Rook theory is a set of pairs, and the set of pairs is basically the same as the arc set of a digraph. But in the language of digraphs, this has been introduced by Chow, and I think even in the language of Rook theory, probably it was new. So, I should warn you that Chow actually did something more general. His power series involved 2 sets of variables. I will only be looking at 1 set of variables, and I'm wondering whether anything I will do can be generalized to 2 sets of variables. So here are the definitions. First of all, I define something that's known to a lot of you. Let me see, maybe to all of you, maybe not. Let me quickly go over this. N is a non-negative integer. I is a subset of, so this notation means the first n positive integers. Then Li, n is the sum of all monomials of the form xi1, xi2, xi dot 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 xin, where the i's are weakly increasing, and I mean weakly increasing positive integers. And furthermore, every time the subscript is in the subset I, it's not a weak increase, it's a strict increase. So basically, any chain of less or equal and less than signs under the summation sign can be implemented with an appropriate n and appropriate I. And now, if I have a digraph D with n vertices, I can define its so-called Redei Berge symmetric function, which I call UD, and that is the sum over all the n factorial many V listings W of such an L function. So what is this thing? Well, n is, of course, n, the number of vertices. This is the set of those i's for which wi and wi plus 1, so the i's and I plus first entry of my listing, form an arc. All right, so I think I should give some examples because this is a little bit too dry. Here is a digraph D. So it has 3 vertices, so it has 6 V listings, which are 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 2, 3, 2, 1. And for each of them, I take this L function. Now, what is this? What is this of this comma Z? Well, I look at this V listing. I see wherever 2 adjacent entries form an arc. So is 1, 2 an arc? Yes. Is 2, 3 an arc? No. And whenever you have an arc, you put that corresponding position in the set. So this set is 1 because 1, 2 is an arc and 2, 3 is not an arc. The next one, 1, 3, 2, gives you the empty set because neither 1, 3 nor 3, 2 is an arc. So you get empty. The next one is again empty, then comes the v-listing 312. And 312, if you look at it, 3.1 is not an arc, but 1.2 is an arc. So you have an arc at the second position, and that gives you the set 2. And the last one is again empty. If you combine the terms, you get this term 4 times. So 4 times this plus this plus this. And now you remember what LIN is. And quite explicitly, it's so for the empty set, all the inequalities are weak. So you get this sum. For the set 1, you get this sum because the first inequality gets made strict. And for the set 2, you get the same sum, but instead of the second inequality sign is strict. So you get this expression.
Darij, I've got a question. So you
Bruce.
seem to be, hey there, Darij, nice to see you. Kakila. So you don't seem to be using a digraph here, right? Because you're just considering whether the two things are connected. Why just
no,
why this for
I mean,
and not for graphs?
No, I mean, this is a pair.
This
So 1.2 is an arc, 2.1 is not an arc.
Okay, so yeah, you definitely are doing it. Gotcha.
Yeah, so when I say two adjacent entries, I mean the left and the right in this order. Sorry, this is a little bit abusive. Okay, so what do you see about this function, this power series for now?
Darij, is this instead of quasi-symmetric, this is symmetric function actually, right?
Yes, exactly. Exactly. And of course, this is a simple example. In simple examples, often things get symmetric. But actually, this is the first interesting thing about it. And I think Richard, I don't actually know who first discovered it, probably Chow. Before I move on to further properties of this UD, let me restate it in a different language. If you don't like the else, here is another way to put it. UD equals a sum over all functions f from the vertex set to the positive integers. You can think of such a function as a coloring of the graph, but it's not a proper coloring, it's just some coloring. Or alternatively, you can think of it as assigning a level to each vertex. So if f of v is I, it means that the vertex v has level I. Either way, so what is the sum? You're summing, this is a monomial where you basically take the product of x f of v over all the vertices. And there is a coefficient ADF, which is the number of all v listings with the following property. The v listing has to be weakly increasing, and every time there is an arc, it has to be strictly increasing. You might remember this from the theory of p-partitions. It's very closely related, and also it might remind you of chromatic symmetric functions. But for chromatic symmetric functions, you would expect strong inequalities everywhere and like no inequalities. So you would not have inequalities between the non-arcs. So it's not quite the p-partition numerator. It's not quite a chromatic symmetric function, but it's close. And there is yet another way to view it. So basically, what do these conditions say? And I'm sorry, this is not a minus sign. This is just a bullet point. So this condition says that you first list all the vertices of level 1, then the vertices of level 2, then the vertices of level 3, and so on. So basically, you're not listing the whole vertex set. You're listing the vertices of each given level, and then you're concatenating those listings in the appropriate order. And the second condition says that as long as you're listing a given level, you cannot have an arc between two adjacent points, the vertices. So on each level, you're listing the vertices of this level in such a way that you don't have an arc. It's like an n-type path. And of course, an n-type path in a digraph, it's a path of the complement digraph. And because you have to list all the vertices of this level, it's a Hamiltonian path. So here is another way to put this. ADF is a product over all levels. So f of v means the set of all levels. Number of Hamiltonian paths of the complement digraph restricted to this level. So at this point, you start seeing the connection because we're now counting Hamiltonian paths. even so we're not just counting them for our original D bar, but actually for certain subdigraphs. And indeed, this is not a coincidence. UD is actually pretty useful for counting Hamiltonian pairs. In fact, if you evaluate UD at 1, so you plug 1 for the first variable and zeros for all the others, you get the number of Hamiltonian pairs, but not of D, but of D bar. The bar is just a little annoyance because, of course, you can apply it to D bar and then you have D instead. It's just a substitution away from what you want. And this proposition is actually pretty easy to prove. If, for example, this else, they become 0 unless the set is empty. If you plug 0 for all the numbers starting at x2. So you only have to care about the listings for which the set is empty. But that means that wi plus 1 is never an arc. So it means that you have a Hamiltonian antipath or a Hamiltonian path of D bar. So anything you can say about UD gives you something about the number of Hamiltonian paths in the digraph. This means you can hope to find a different approach to Redei's Berge theorem, but also to maybe prove something more. Now, of course, what can you say about the UDs? And actually, the answer is quite a lot. There is an addition. So Stanley's EC2 has just come out a month or so ago with a bunch of additional problems to chapter 7, and one of them is about those UDs. There is quite a few properties, particularly when D has some nice shapes, like closed set or incomparability digraph. So, but in this talk, I will talk specifically about a certain question, which is, I think, one of the most general ones, which is about the so-called P expansion. What is the P expansion? Well, the thing you know. So you take the power sum symmetric functions. Pk is x1 to the k plus x2 to the k, and so on. And you try to expand UD as a polynomial in this Pk. The first theorem is you can do it. UD is a polynomial in the power sums with integer coefficients. So of course, this means that UD is symmetric, but it's actually stronger because integer coefficients. Not everything symmetric is a polynomial in the piece with integer coefficients. Now, which polynomial? And it turns out that this has an answer, a pretty nice combinatorial answer, but it needs a little bit more notation. So we have a digraph D, and SV will mean the symmetric group on the set V, so the group of all permutations of the vertices. If sigma is such a permutations, then psych C means the set of all cycles of sigma, and we also let P type sigma to be the product of. Okay, so let me just put it simply. So if a permutation has cycles of lengths A, B, and so on K, then P type sigma is PA, PB, P dot dot PK. So basically you multiply a power sum for each cycle, and the subscript is the length of the cycle. And of course, as usual in combinatorics, you have to include the one cycles. So the degree of this is n. And also I want to say that a cycle of sigma is a D cycle if it is a cycle of the digraph D. So basically, if for every I on the cycle, the arc that moves out of I, so I comma sigma I, that is an arc of the cycle, of the digraph. And here is the first formula for UD. This formula is true for any digraph. And it says basically this: UD is the sum of P type sigma multiplied with a certain sign, and the sum ranges over all permutations of V, for which each cycle of the permutation is either a cycle of D or a cycle of D bar. So in other words, if you look at every cycle of sigma, either all its arcs are arcs of D, or all its arcs are arcs of D bar, which means that none of its arcs is an arc of D. So it's like one end or the other. If you have an arc of D and an arc of D bar on the cycle, it's not allowed. you have to, basically, it has to be either extreme. Now, what is the sign? This sign, okay, let me say it again. Let me simplify it a bit. This is the sign is the number of odd length. No, the number of even length cycles of sigma that are D cycles. I invite you to ignore the sign for the time being, and just look at a few examples. Here is the example we started with, the digraph D and its complement. I claim here that D has no cycles, but actually this is wrong, because it has the trivial cycles 2 and 3. Sorry, I have to fix a lot of things. Anyway, D bar also has some non-trivial cycles, 2, 3, 3, 1, and 1, 3, 2. I think it's easy to see that there is no others, yeah. And I put a tilde here to signify that I mean a cycle, not a path or a list. Okay, so now let's see which permutations of V. There is 6 permutations in total. Which of them have this peculiar property that every cycle is D or D bar? Well, for example, the transposition 1, 2 does not have this property because it has a cycle 1, 2, and that is neither a blue cycle nor it's neither a cycle of D nor a cycle of D bar. It has one arc from D and one arc from D bar. This is like the middle ground that we want to avoid. So this transposition will not be part of the sum. But what will be part of the sum? Well, there will be 4 addends. One addend is the identity permutation, which is always an addend because the identity permutation has only trivial cycles, and each trivial cycle is either blue or red. It has only one arc. There is this here. This permutation in one-line notation here, it has only one cycle, and that cycle is all red. 2, 3. Okay, no. So one-line notation says 2, 3, 1, but as a cycle, it's 1, 3, 2. So 1, 3, 2. I think. Ah, okay. I think I'm also wrong here. Please read this as 3, 1, 2. So this has a single cycle, and that's red. 1, 3, 2. This has 2 cycles. It's a transposition, so there is a cycle 2, 3, and the trivial cycle. The trivial cycle is red, and the cycle 2, 3 is also red. So both of them are red. So you get another term here. And 3 to 1, that's also a transposition where you also have this property. 1, 3 is a red cycle, and 2 is a blue cycle. So you got those 4 addends, and their phi sigmas are 1. Why are they 1? Basically because there are no non-trivial D cycles. If you look at the digraph D, its only cycles are trivial. So in particular, they all have odd lengths. So the sign there is never any chance for the sign to become minus. And finally, p-type sigma. This is the cycle type, so it's like, this is the identity permutation, so it has 3 cycles of length 1, so it's P1, P1, P1. This has P3, P2, P1, P2, P1. And so our theorem yields this expression for UD. Okay, so this is a good example to follow. Are there any questions?
So your sign is basically just the usual sign of the permutation, but just restricted to D. You only take the cycles that lie in D, right?
That's probably a good way to view it.
Yeah.
Yeah, I think so.
Because, right, you're just the length of cycle minus 1, that's the length
Yes.
in Brouillard terms.
Yes, exactly. So I restrict it to the subset where all the arcs are in D. And that,
then
yes.
to that permutation.
Thanks, Bruce.
Not a problem.
Yeah, let me actually write this down. Yeah.
And also,
So
I wanted
that's,
to ask,
Mhm.
oh, sorry. And the only difference between UD and UD bar is the sign?
Yes.
Alright.
This will actually be this will be on the slides.
I see, thanks.
Very, very, very good observation. So let me quickly go over another example where I have, so this is D and this is D bar. The only interesting thing about this other example is that now you get a minus sign. Why? Because 3 to 1, this is a transposition 1, 3. It has a blue cycle 1, 3 and the red cycle 2. And the blue cycle has even lengths. So it does contribute a minus, so it does contribute something to this exponent. And this exponent becomes odd, so this whole thing becomes a minus. And the result is that UD equals this. So if you've been wondering whether UD is always P positive, it's not always P positive. But nevertheless, this is a nice theorem. And in particular, as Marino said, this yields Berge theorem, because if you take the sum for D and for D bar, the sum ranges over the same sigma, and the addends only different sign. But there is a few more things that come out of this. First of all, if every D cycle has odd lengths, then the signs are always plus. So you simplify this as follows. And that means in that case, it is P positive. It's a polynomial in the P's with non-negative integer coefficients. But even better things can be said if D is a tournament. In a tournament, you get a formula where you can be, basically you're able to bunch certain terms together. And I realize I'm using something that I have not defined. Sorry. So the sum is now going to be over a smaller set. It's going to be over all permutations where each cycle of sigma is a D cycle, not a D bar cycle. And then, okay, here it is. But then instead of P type sigma, you have an actual power of 2 times P type sigma. And the power of 2 is 2 times, so 2 to the power of the number of non-trivial cycles of sigma. By non-trivial, I mean not just a single element. And if you look at this formula, you realize that every pi, so basically every time you have a cycle, you have pi times 2 if the cycle is non-trivial. So it's not just a polynomial in the pi's, it's actually a polynomial in the odd pi's, and each of them except for p1 has a 2 in front of it. So this is a pretty small sub-algebra of the symmetric functions. Oh yeah, and I should say all the cycles have odd lengths as well. So this is a pretty restrictive sum. So this sub-algebra, I think it's known from the theory of Schur Q functions. It's not exactly a new thing. Nevertheless, I have no idea what this actually has to do with Schur Q functions. I think this is a mystery that some people are trying to understand right now. Why is this in the sub-algebra generated by the Schur Qs? Well, it is. It's much less clear why. And of course, you can use this to prove Redei's theorem now, because this power of 2, if you look at it modulo 2, this power disappears unless the exponent is 0. But the exponent is 0 only if sigma is the identity, so you're left with a single stupid term, p-type identity. And that is p1 to the n, which is very easy to analyze. Now, let's say a few more things about p-positivity. So this corollary says that UD is p-positive if every D cycle has odd lengths. But actually, it's p-positive in various other cases too. So here is a more general case where it's p-positive. It's p-positive when the digraph has no cycles of length 2. Go figure. As this is not a condition I expected to see anywhere. This is a strange condition. Nevertheless, it works. In this case, UD is the sum of p-type sigma, where sigma, so this is the old condition. And now this is a mouthful, but this is the other condition we need. No even length cycle of sigma is a D cycle or a reverse D cycle. Even that does not cover all the p-positive UDs. There are more. So I don't know whether we can even hope for like an if and only if. Like UD is p-positive if and only if. I don't know. But this is a pretty good if already. Now, let me say a few things about how the theorems are proved. The proof is actually pretty long in the paper, and I'm trying to simplify it. It's part of why it's taking so long to finish this paper. So quite a few ingredients in there. Let me start with a simple lemma. You have a finite set V and the permutation sigma, and you sum over all the basically colorings of V that are fixed, that are preserved under sigma, this monomial. The result will be P type sigma. This is an easy exercise, and I'm pretty sure I've seen it somewhere. I just don't remember where. I think it's like involved in Polias theory, sort of implicitly, but it's simpler than anything you see in Polias theory. Now, using this theorem, using this lemma, it is not too hard to boil down the first main theorem to the following lemma. So you have a digraph and a coloring. Okay, let's not call it coloring. Let's call it a level assignment. So this assigns a level to each vertex. Then ADF, so this is basically the number of Hamiltonian pairs of each level set multiplied over the level sets equals this alternating sum. This is the sum over all sigmas where each cycle is either a D cycle or D bar cycle that are preserved on all sigmas that preserve the levels. In other words, it's not a permutation of V so much as a permutation of each level set separately. And then you take this -1 to the 5 sigma that we've already seen. Okay, so this is basically what we have to prove. And this is a combinatorial statement, purely, no power series or whatever. But if you state it like this, you actually see that F doesn't really matter. This is like a statement for each single level, and then you multiply it over all the levels. Because if you look at this closely, you will see that it basically sigma decomposes into a sigma j at each level j, and then everything here is a product. So you can forget about F, and you can just work at a single level. So the lemma becomes the following. Let D be a digraph with n vertices. Then the number of hemps of its complement equals the sum of -1 to the 5 sigma, summed over all sigma, where each cycle is either a D cycle or a D bar cycle. This looks like a pretty nice case of some kind of direct inclusion-exclusion, maybe sign reversing involution. And I'm hoping that it actually is such a case. So it would be great to have like a big set with a sign assignment. And if you cancel things in one way, you get this. If you cancel them the other way, you get this. And then you conclude that they're equal. So a Seilberger or Sagan style argument. For now, we don't have such an argument, but it's pretty close. It just has multiple. It's just more complicated than that. It involves like multiple up and down cancellations. Now, this gives main theorem 1, the case of an arbitrary D. Now, main theorems 2 and 3 follow from main theorem 1 by bunching together addends. So basically, if you look at main theorem 1, P-type sigma, basically different permutations often have the same cycle type. And the easiest way to get permutations of the same cycle type is you start with a permutation and then you pick certain cycles and reverse them. So instead of going like 1, 2, 3, 4, you go 1, 4, 3, 2. If you do that, the cycle type stays the same. And this thing, this changes in a predictable way. Basically, if you reverse a D cycle or a D bar cycle that is even length, this sign flips. And if you reverse one that is odd length, the sign stays the same. And so you decompose the sum into orbits, and then you have to see which of these orbits have equally many plus and minus signs, and which of these orbits have basically only plus signs. There are no other options. And then some orbits have pluses and minuses, and they cancel out. And the other orbits have only pluses, and that's where you get a power of 2. Now, the details actually have to be checked. It's not exactly obvious, but it's also pretty straightforward if you understand what you're doing. So in the tournament case, these are the powers of 2 that you get, and the zeros of course disappear. And in this main theorem, you also you get this, but you have to be more careful about which addends you bunch together. a lot of them cancel, and the rest are staying in trivial orbits. Now, these formulas, so we can use these formulas to prove Berge and Redei, but we can actually prove something stronger than Redei. So remember, for a tournament, the number of Hamiltonian paths is odd by Redei. But let's look at it modulo 4. Then it is congruent to 1 plus 2 times this number of odd length non-trivial D cycles. Non-trivial simply means that the length is positive, greater 1. And odd length means that length is odd, of course. So this is not actually hard to prove using the second main theorem. It's just you have those powers of 2. Instead of looking when they're 1, you have to look at when they're 1 or 2. Everything higher is divisible by 4, and then you analyze those cases. Can this be done can this be done directly graph theoretically? I don't know. All I know is I have not seen this in the literature. Maybe I haven't looked closely enough. And so there are a few things that haven't made it on the slides. One of them is a formula for the antipode of UD, because UD is a symmetric function. A symmetric function has an antipode. And guess what? The antipode of UD is UD bar, up to sign. But this is well known, and it has been proved 4 different times in the literature. So back when Chow invented his functions, somehow nobody came up with those formulas, but people proved the antipode in several different ways. So that wouldn't be a new result. And yes, you can use it again to prove Berge theorem, but that's not easier than the other proofs. Are there any questions so far? Okay, if no,
Actually, so you've got all these nice results about the expansion and the p basis. Are there nice things you can say about expanding in other bases?
So I wanted to talk about it, but every time I think, I realized I have pretty much nothing to say about it.
Oh, okay.
So
That answers my question.
Yes, Richard can say more. Several people have tried to expand them in the Schur basis, and the result every time seems to be it's almost never Schur positive.
Oh dear.
So I could of course look at the appropriate exercise in Richard's text, but I think Richard probably remembers it better.
Yes.
Yes.
There's a handful of special cases where you can prove Schur positivity. For instance, there's a case where you get the chromatic symmetric function of the incomparability graph of a, semi-order. That's in fact H positive. Well, in this context, H positive. So, well, I should twist it by omega, so it would be even more than Schur positive, H positive. And there's some there's some other special situations, but it seems in general it's not Schur positive.
Oh, I see the question. Does antipode mean omega? Yes, it does. It is omega up to sign. And the sign is very predictable. It's -1 to the degree. Yes, omega is probably the better thing to talk about. So I'm showing what I'm showing you right now is actually Richard's additional problems, which are now part of his actual book. So if X, so this is the digraph, which is basically a directed path. In that case, the U is a certain sum of Hooke-Schur functions with explicitly computable coefficients in front of them. That is a Schur positive case. And I don't not many other Schur positive cases are known. The other one comes from this incomparability graphs. So here you have the increasing relation of opposites. Okay, so let me mention something else. To some of you, it will look like a distraction. To others, it will look like the right thing to do. I'm a bit driven myself. So is this all about digraphs? Well, you might say yes, you might say no, because there is a way to generalize it where you replace the digraph by a matrix. So here is, so imagine you have a finite set V with n elements. This is from the preprint. Now, for every pair of two elements, you fix an element Ti, where A is the pair, so basically Tij for each pair, I comma j. And then you set Sij is Tij plus 1. And now you define the following power series. You sum over all V listings, you sum over all weakly increasing sequences of n positive integers, this monomial times the product of the S's corresponding to the pairs Wk, Wk plus 1, where the corresponding integers are equal. So this is a formal power series now defined over K, where K is the base ring. So the T's come from some arbitrary commutative rings. So for example, for a two vertex, well, basically when V has size 2, you get this function. And gosh, I think I have a typo here. N equals 3. So for 3 vertices, you get this here. And again, you can see that all of these things are P integral. And if the T's are minus 1s and 0s, you get the digraph case. So you get you get this UD. And again, there is a P expansion, which by the way is P positive, but this is like this P positivity does not entail the original P positivity, because to get a digraph, you have to plug minus 1s in there. And this P expansion can actually be written out pretty nicely as a sum again over all permutations. For each permutation, you take a product over all the cycles. These are the arcs of the cycle. And so you multiply the SA minus the product of the TA. So, and if you plug in that case, you get the first main theorem back. So this is a pretty nice generalization. However, it's not much of a generalization. In fact, you can actually derive it from the digraph case, because this is a multilinear polynomial. So none of the variables occurs with a higher power than 1. And if you want an identity between two such polynomials, if you can prove it for minus 1s and 0s, you can prove it. It automatically follows for all the possible inputs. So this is not really a strong generalization. I also do not see any, like, I don't know whether there are any ways to generalize the other two main theorems, but it doesn't look like there are. So maybe this is a bit of a dead end, but I wanted to have it mentioned. Okay, so thanks a lot to Richard for well, this beautiful problem and for your part of the work. Mike Zabrocki has actually suggested this last generalization to me. Thanks, Anna, for the invitation, and thanks to all of you.
Thank you, Darij. Very nice talk.
I mean, I should also thank my university for giving me an opportunity to teach graph theory. Every time I teach graph theory, I discover something, some new little thing, and this is one of those.
Very nice. Any questions for Darij?
Yeah,
Thanks,
I have
Sheila.
a question.
Mhm.
Quick question. Darij, in your last deformed multivariable case, okay?
Mhm.
The coefficients of the P's, is there any structure to them? The T's.
What do you mean by the coefficients of the T's?
The coefficients of the P's. If you go back a couple of slides back, you define the UTs, right?
Is this here?
Yeah.
So C arcs gamma is the arcs of a cycle. So if a cycle is, for example, 1, 2, 3, 4, then C arcs gamma is 1, 2, 2, 3, 3, 4, 4, 1. And then I multiply the respective S's minus the product of the respective T's. So it's going to be, so remember that an S is just the corresponding T plus 1. So it's like T1, 2 plus 1 times T2, 3 plus 1 times T3, 4 plus 1. Maybe I should really start writing this down. annotate text. So if gamma is 1, 2, 3, can you see this, what I'm writing?
Yeah.
Yes.
So C arcs of gamma are 1, 2, 2, 3, 3, 4, 4, 1. So the factor is S1, 2. I'm gonna skip the braces. Minus is the same, but with T instead of S. And as you remember, the S's are the T's plus 1. So this is really C1, 2 plus 1, C2, 3 plus 1, and so on. And of course, if you expand this, this is the leading term. So it's just this expansion minus the leading term. Oof, this is probably not very readable behind all the other text. Maybe
Yeah,
let
it's
me do
okay.
it. Yes, sorry. This is a bit better. No,
That's okay.
no. Okay, honestly, I have no idea how this annotation works. I think it changes all the time. Any more questions?
Actually, I have one. So
Mhm.
you put 1 to the original UD, and then all zeros, and then you can just count the number of hems, right?
Yes.
And so how about if you put other numbers? Like what are you counting if you put other numbers? Like say for example, I put 2 ones, or put 3 ones and zeros. Does that mean anything or?
Oh, okay, that's a good question. It's some kind of Hamiltonian path where you decompose the graph into 2 pieces and then each separately.
I see.
Yeah, it's worth playing around with this.
And even if you put something like -1, would that actually do something? Like, I don't know, like, do you always have to
Maybe.
just put 1? Okay. And also I have another questions about like, you proved it mod 4 by just looking at instead of, because how you look at it is 2 to some power, and then so if the
Sorry,
power is big. Oh, sorry. No, yeah,
your
this one.
connection got lost.
Oh,
Yep. Oh, sorry,
okay.
it's my connection actually.
Okay. No. So like, you proved that this mod 4 by looking at like only 2 to the power where the power is 1 or 2 and analyze those cases, right? And
Yes.
so how about mod 8 and then any 2 to the power? Is that like much more harder, or like is it because the right hand side is not like a nice expression?
Okay, I mean, you can keep analyzing it, but eventually it will get more and more complicated. So the problem is the permutations with only one non-trivial cycle are the cyclic permutations.
I
So
see.
they're basically, they are cycles. Whereas a permutation with two non-trivial cycles, it's already like pairs of disjoint cycles, and you have to argue about what it means. But yes,
I
you can do
see.
it.
Thank you.
Darij, a question for you. In your surprise statement, in here, there's a lot of odd everywhere. And in this congruence, you have 1 plus twice of a number, mod 4. Is the number in parentheses itself odd number?
Probably not generally. I think it can be either. I mean, Z might have no cycles, in which case it's 0, but Z can have one non-trivial 3 cycle, in which case it's 1. And I don't think it can be predicted this easily. I mean, here you have different cases here. 3 vertices, it can be 1, it can be 3. Yes, and of course this gap with there is no 7 here. That's of course an instance of this result by mass overflow people. I wish I could reference them properly, but one of them is just a nickname, and the other is somebody with a name. Boff and Gordon Royal. And this is a link, by the way, you can click it.
Thank you. Any other questions?
Yeah, I have one. So in your definition of UD as a sum of fundamental quasi-symmetry function over descent set, right? Have you tried, say, using cyclic descent? Like,
Ooh. Okay, this is a whole extra can of worms. So you to get Hamiltonian cycles out of it, I assume. So the problem is with the number of Hamiltonian cycles, I'm not going to say it can be anything, but it certainly can be 0 or 1, at least. Which may, or wait, is this, yeah, it can certainly be 0 or odd. So I don't expect to get a modulo 2 congruence for it, but maybe something can be done with it.
Any other questions? Or if not, then let's thanks Darij again. Thank you so much.
Thanks, Anna.
Sure. So I will post the recording by tomorrow, and we'll resume on Thursday, same time.
Yep, and from what I understand, the best thing is to give a completely different topic.
Sure.
Unless there is much interest in a little bit in the few details that remain from this.
No problem. You are the host, so you are the boss.
Perfect.
All right.
Thank you.
Sure.
See you.
See everyone. Bye.